world of constant shortages, one quantity remains in abundant supply. It's called entropy.
The science of thermodynamics is based on 4 fundamental postulates or axioms which are called the 4 laws of thermodynamics. Of these 4 laws, the second law was discovered first, and the first law was discovered second, and the third to be discovered was called the 0th law, and the 4th law is called the third law. Now, all of that makes perfect sense because thermodynamics is the most implacably logical of all the sciences. Let me tell you briefly what those 4 laws are. The 0th law just says that the idea of temperature makes sense. The first law is the conservation of energy. The second law is the entropy principle. And the third law says that there is a temperature so low that it can never be reached. From these 4 laws, people have deduced not only the properties of matter, but the ultimate fate of the universe itself. Now, if we're going to get anywhere on that today, we had better get started.
Chalkies Billiard Academy, an inner sanctum of sorts, where beyond the harsh glare of the limelight, celebrities of sport, dandies of high society, and captains of industry gather to pursue a common interest. One may wonder how these gentlemen manage to keep their names out of the newspapers, to say nothing of the learned journals. And the casual observer may ask, what are nice guys like these doing in a place like this? But to those in the know, their purpose is obvious: to investigate the laws of thermodynamics. But why Chalkies? Partly, of course, it's the ambiance, which is the last word in understated elegance. But that goes without saying. Mostly, it's the equipment, the specially called for apparatus that in the interests of science, Chalkies always seems to have on hand. Even now, 2 distinguished scientists hold beakers.
Due to mature subject matter, the following experiment should not be viewed, much less conducted, without parental consent.
Held with the greatest care, each beaker contains a small amount of experimental fluid, which unfortunately is an acquired taste. However, before things began to get out of hand, the fluid was poured into the beakers at a temperature of 295 kelvins, and with scientific precision, several geometrical cubes of crystalline H2O were added. Initial temperature of the crystals, 273 kelvins. As time passes, heat from the warm fluid flows into the cubes, but the ice fails to warm up in response. The cubes don't melt at once, which stirs up a scientific controversy. And of course, this calls for more tests. During 126 experiments, but who's counting, none of the Chalkies scientists can find a single instance of a warm ice cube. But on the other hand, they have found a dilution of the properties of the experimental fluid. The ice, staying at a constant temperature of 273 kelvins, melts into liquid water as heat flows into it. What accounts for this strange behavior in Chalkies, or for that matter, everywhere else in the world? Eventually, of course, ice melts. But along the way, in its solid state, why won't it warm up? In any case, in the end, the ice, the experimental fluid, and in fact everything else, reaches a state of equilibrium. Somewhere, at least in theory, there's a heavenly state called equilibrium. But in the real world, equilibrium is hard to find. On a Polynesian isle, the planet cranks up and liquid fire bubbles from down below. And in the polar center of the Arctic Ocean, the world's original ice machine works around the clock. In the deep and darkest heart of Equatoria, the sun sears a savanna with a relentless regularity. And a shout away, liquid thunders to the rocks below. Indeed, from the beginning, through the middle, and to the ends of the earth itself is a great machine. A factory that never runs down, never takes a break or goes on strike. The engine of nature, a powerhouse, driven non-stop by the limitless energy of the sun. Whether as trade winds of the great oceans, or the diesel engines of the great ships that ply them, all engines work because heat in motion can set matter into motion. For several hundred years, the heat engine has gone far and wide. But past or present, the heat itself goes only one way, from high to low temperature. The existence of any engine on Earth, including the Earth itself, depends on one of its parts working at a higher temperature than another. In nature's engine, for example, powerful currents are driven through the Earth's atmosphere by the difference between the equator's temperature and the temperature at the poles. From pole to pole and engine to engine, the principle is the same. In this vehicle, it's the difference between the temperature of the exploding gasoline and air in its cylinders and the circulating water of its cooling system. Steam engines operate between the high temperature of the firebox and the low temperature of the atmosphere. The bigger the difference in temperature, the hotter in one part of the machine, the cooler in another, the better the engine works. But if the fuel stops flowing and the hotter part of the engine is allowed to cool down, the engine grinds to a halt. And obviously, that can spell trouble. If every part of the engine has the same temperature, if all motion ceases and there's no vitality left, the engine reaches its final state, the state of equilibrium. From a scientific perspective, then, what's the picture?
In this molecular dynamics calculation, each pair of atoms is programmed to interact with a realistic interatomic force.
So then what really happens when a warm body is brought into contact with a cold one? Thermal energy spreads from warm to cold until both bodies reach the same temperature. This is the state of thermal equilibrium. At first glance, thermal equilibrium seems different from the mechanical idea of stable equilibrium, which keeps a body safe from falling. But take a closer look. When a falling body hits the ground, each bounce is smaller than the last. Why? Because the kinetic energy of the body as a whole becomes transformed into the chaotic motions of the atoms that compose it. And that process is very similar to heat flowing into a cold body, and the end result is the same. All of the available energy eventually becomes shared out as kinetic and potential energy of random motions of all the atoms. Therefore, although the idea of equilibrium seems the ultimate in peace and serenity, that view hides the seething motion of the atoms within. So understanding equilibrium is a matter of perspective, of seeing within, and of seeing beyond. Because equilibrium is a state in which all temperatures are equal, it's a place where no machines operate. No geysers spray, no volcanoes erupt, no water falls. No big engines want to do any work, and no little engines can. Everywhere, nature seems impelled toward the state of equilibrium. Hot bodies and cold ones striving toward the same temperature, and falling bodies turning perfectly good work into useless heat. From the physicist's point of view, when nature tends to behave in such a universal fashion, there must be a scientific explanation, and there is. The explanation began as an idea, of course, an idea for the construction of a better steam engine.
There was a young man named Carnot, whose logic was able to show, for a work source proficient, there's none so efficient as an engine that simply won't go.
C.D. Carnot's greatest ideas never worked, and in the real world probably never will. Yet he had the desire to create an engine as perfect as nature would permit, and the logic to come pretty close.
Given a difference in temperature, a high temperature, T sub I, and a low temperature, T sub O, Carnot designed a perfect abstraction. The Carnot engine takes in heat, Q sub I, at the high temperature, turns some of it into work, W, and expels the rest, Q sub O, as heat at the lower temperature.
Because the Carnot cycle could run just as well in reverse, it was the picture of the ideal engine, the most efficient machine the laws of nature could possibly permit. But with Carnot's early death, his ideas, practically ignored from the beginning, seemed destined for oblivion. And that's probably where they would have ended, had not two great scientists taken an interest in Carnot's theory. Rudolf Clausius, a German physicist, and William Thomson, the Glasgow professor of natural philosophy, who would become Lord Kelvin, rescued Carnot's original writings, and from these very pages brought forth the science of thermodynamics. Within Carnot's reasoning, Clausius and Thomson saw an amazing fact, and they saw it in terms of an astonishing mathematical simplicity. In Carnot's ideal engine, the ratio of the heat taken in to the heat wasted was the same as the ratio of the two absolute temperatures needed to drive the engine. In other words, and this was the ideal that stemmed from Carnot's imagination, something that goes in is the same when it comes out. If it's not the heat, and if it's not the temperature, what is it? It's the heat divided by the temperature at which it flows. And according to Clausius, that's entropy. In a Carnot engine, some entropy flows in at high temperature, does its job, and the same amount of entropy flows out at low temperature. So an ideal engine not only conserves energy, it conserves entropy as well. That's the ideal. But what about the reality? In the real world, with the clanking, hissing, whistling, puffing engine, what really happens? For one thing, all engines conserve energy. The work equals the difference between the heat in and the heat left over. But using the same temperatures, a real engine does much less work than Carnot's ideal. It does less work and leaves more heat to release. So even though the entropy that flows in might be the same as Carnot's, the entropy that flows out is bigger. That's an amazing fact. The entropy that flows out of a real engine is bigger than the entropy that flows in. Could this mean that real engines create entropy out of nothing? As a matter of fact, yes. That's because in real engines, heat flow isn't isothermal. Power strokes aren't adiabatic, and there's always friction between moving parts. No matter what the final product will be, all real engines manufacture entropy. No matter the conditions in the workplace, the supply of entropy always increases. And no matter the workplace, humans don't own the patent on the manufacture of entropy. Day in and day out, Mother Nature's machines crank out entropy, and nobody on Earth can compete with her output. Every body of matter, everywhere in the universe, contains a certain amount of entropy. And although it isn't always easy to tell just how much entropy a body has, it isn't too hard to determine when entropy flows from one body to another.
If heat flows out of a body at temperature T, the entropy of the body decreases by Q over T. If heat flows in at temperature T, the body's entropy increases by that amount.
Throughout the cosmos, when and where heat flows, entropy flows with it. All engines extract heat from somewhere, the sun perhaps, or the boiler of a ship. Use some of it to do their work, and then release the rest. Where the heat's released doesn't matter too much, not in the big scheme of things. It flows into the atmosphere, the sea, anywhere that's cool and too large to be affected very much by the flow of heat. Engines designed by humans operate pretty much the same way as the ones Mother Nature cooks up. As long as heat flows from a high temperature to a lower one, things keep rolling. And as long as there's fuel, coal or oil or wood or whatever works, they'll keep rolling. But if the fuel is cut off, the heat ceases to flow. The body cools, its temperature lowers little by little. And when a body finally has the same temperature as its surroundings, it's in a state of equilibrium. As long as heat flows, as long as a warm body is warmer than the cool one, entropy will increase. And it will continue to increase until nothing else can possibly happen. The state of equilibrium, and should that happen, entropy would increase no more. In other words, the state of equilibrium is the state of maximum entropy. All of nature's processes can be seen as a constant drive to increase entropy, all the time throughout the universe. And though these facts have been well established in most scientific circles, a handful of dedicated researchers will not leave well enough alone. Perhaps that's because one fact still puzzles the most curious. Though ice melts as heat flows into it from the experimental fluid, the ice doesn't warm up while there's any solid left. Why?
A flow of heat causes the transformation of ice into water at a constant temperature. Therefore, in changing from ice, the water's entropy is increased.
And so, water is a state of higher entropy than ice. In fact, any solid is a state of lower entropy than the same matter in liquid form. Liquid is a more disordered, chaotic state of matter than solid is, and it has a higher entropy. On land and sea, or sea on land, or indeed anywhere in the universe, increasing entropy means increasing disorder and randomness. And the ice itself? It's a crystalline solid, a state of matter in which molecules exist in a neat, geometrically symmetric framework. In a solid, when the atoms cluster in the most favorable configuration, the molecules are arranged to reduce their potential energy to a minimum. But water's a very different picture. Remember, liquid molecules are chaotic, disarranged, scattered, and disorganized. Obviously, liquid molecules don't minimize their potential energy as the solids do. So, liquids not only have more entropy than solids, they also have higher potential energy, and therefore, more total energy. To melt or not to melt, that's the question. And if the dynamic isn't quite yet as clear as crystal, in this case an ice crystal, look at it from the ice cube's point of view. If the ice melts, it becomes water, a state of higher entropy, and that's good, because nature just loves to increase entropy. But hold it. Before melting, before becoming water, the ice must also increase its energy, which requires extracting energy from the rest of the universe. But if energy, in the form of heat, flows out of the world into the ice, it reduces the entropy of the rest of the universe. And that's not good. How bad is it? Well, the entropy of the rest of the world decreases by the energy that flows divided by the temperature. Remember, nature always wants to increase entropy. In this case, the entropy of the ice, plus the rest of the universe. If the temperature is very small, it's very bad indeed. Melting the ice would cause a big decrease in entropy of the entire universe. If the temperature is big, it's not so bad. The combined entropy increases when ice melts. That's why, in the grand scheme of things, ice never melts at low temperature. And ice never exists at higher temperature. Meanwhile, back in Chalkies, to say nothing of the universe as a whole, there's a temperature somewhere in the middle. A temperature at which neither ice nor water is favored. And it's the only temperature at which both ice and water can exist together, which explains why these scientific beakers will never warm up until all the ice has melted. So in the scientific language of Chalkies, the quantity nature strives to maximize is not merely the entropy of the ice. At a given temperature, it is entropy minus the energy over the temperature of the ice.
As energy minus temperature times entropy of any sample gets smaller, the entropy of the entire universe gets bigger. E minus TS is called the free energy.
And although there really is no such thing as a free lunch, there's plenty of free energy. And every bit of matter in the world makes its own share of free energy as small as possible. And that's what it takes to maximize the entropy of the universe. So within the confines of a scientific beaker, as well as throughout the universe, the law of increase of entropy drives matter from order to disorder. For some time, some have thought that the increasing entropy of the universe is driving the universe itself toward the ultimate state of disorder. They call it the heat death of the universe, and it's not a pretty sight. It's a provocative notion, dangerous to say the least. So the question remains, will all this increasing entropy plunge the universe into a state of total chaos? If so, it won't be the first time that the fate of the universe has been discovered in a glass of scotch on the rocks.
And so, the entropy principle helps us to understand not only the efficiency of steam engines, but why liquids freeze at a certain temperature and solids melt at a certain temperature. But there are some people who believe that it has an even more profound meaning. They believe that the entropy principle defines the direction of the flow of time itself. Let me try to explain. Suppose it were possible to see a collision between two atoms. You might see one atom come in like this and then go out like that, and the other atom comes in, collides with it, and goes out in that direction. Now, if you had a movie of that event, you would not be able to tell whether the movie were running forwards or backwards. Because at the microscopic level, the law of entropy doesn't apply, and the laws of physics work equally well forwards and backwards. According to the laws of physics, time doesn't have a definite direction at this level. But suppose instead you were to see somebody drop a ball from a tower. If you had a movie of that, you'd be able to tell instantly whether it was running forwards or backwards, because when it's running forwards, the bounces of the ball get smaller each time it bounces. If you saw the bounces getting bigger and bigger, you would know immediately that the film was running backwards. Now, what's happening in that case is that the energy of the ball is turning into heat, and that increases the entropy of the universe. And you know, without anybody having to tell you, that the correct way to run the film is in the direction of increasing entropy. And so that defines the direction of the flow of time. And so there are some people who think that the second law of thermodynamics defines the direction of the flow of time. There are others who say that the second law is a mere tautology. Entropy increases with time increases with entropy, so what else is new? Well, I don't feel that way. I think I understand perfectly which way time flows, and I think I know that our time is up. So, I'll see you next time. Or, if entropy should decrease, I'll see you last time.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.